morning students, I am Chaitanya, Assistant Professor in Mathematics, working in Institute of Aeronautical Engineering located at Dundigal, Hyderabad. Today we are going to discuss the Gaussian distribution and its parameter and properties. Okay, we are under the course curriculum Probabilistic Modeling and Reasoning, and we are discussing the second module, and today's lecture is on Gaussian distribution part 1, which is nothing but properties, definition, and some theorems related to Gaussian distribution. Okay, now, so as I just explained in the last class, Gaussian distribution plays a vital role in machine learning as well as dimensionality reduction, especially. Okay, so that is what that is why we are concentrating on this part, that is Gaussian distribution, because every data set is like a collection of points, and it will have some mean and variance. It will have some spread over the space, and it will have some distribution, probabilistic distribution if you plot it on an xy plane, and probably the distributions will be approximated by Gaussian distributions, and Gaussian distributions in turn will help us to reduce the dimensions, and that is called dimensionality reduction. Okay, that is why we are very interested to learn this concept. Now, first let us look into the definition of Gaussian distribution. Generally, Gaussian distribution is very popularly known as normal distribution. Okay, so Gaussian distribution is nothing but the name which is familiar with the normal distribution. Okay, in statistics we call it as normal distribution. Of course, you might have come across this in your probability and statistics curriculum. Actually, it is proposed and developed, more worked, more enhanced by Carl Friedrich Gauss. That is why it is named after him. That is why it is called Gaussian distribution. Now, let us look into the definition of the density function of Gaussian distribution. Okay, the Gaussian distribution is a continuous random variate whose density function is given by 1 by sigma root 2 pi e power minus 1 by 2 into x minus mu by sigma whole square, where x is any real, and mu comma sigma are parameters of the distribution, and mu can be any number between minus infinity to plus infinity, but sigma strictly a positive real number. So this is if a random variate follows this having this function as its density function, then that variate is known as normal variate or Gaussian variate. Okay, so the density function of Gaussian distribution is nothing but f of x 1 by sigma root 2 pi e power minus half x minus mu by sigma whole square, where x can be any real starting from minus infinity to plus infinity, but sigma should be a strictly positive real, where mu also can be any real. Now, mu and sigma are fixed parameters. Okay, and we are going to reveal their actual relation with the normal distribution. That means how they are parameterized into normal distribution, that we are going to discuss in the coming properties. Now, we are interested to look into the properties of this normal distribution. Okay, its graph and its properties. So here let us just mention few mathematical things. That is, pi value, it is nothing but 3.14, so on. It's nothing but the ratio between circumference and diameter of a circle. You know that, and E is also an irrational number which progress like this 2.718, so on. These two are irrationals which are used in the normal distribution, the density function, and here we are going to prove that the mean, that is p of x, that is the expectation of the normal distribution, is going to equal to mu, and variance is going to be equal to the sigma square. Okay, so that means we are going to prove that mu and sigma are nothing but the mean and variance of the normal distribution. Okay, that is what we are going to establish. So in general, any normal distribution whose density function is 1 by sigma root 2 pi e power minus 1 by 2 x minus mu by sigma whole square can be represented as a normal distribution with mean mu and variance sigma square. Okay, this is a representation. Now, yes. So generally, we'll use this normal distribution to calculate the probabilities in the following cases. To assess the probability of a group of students varying between 160 inches to 180 inches. That is first. And to measure the weights of some students of some apples, some fruits varying from 100 kgs to 200 kgs, okay, or exceeding 250 kgs or less than 200 kgs, and intelligent quotient of a group of students may lie more than above than 150 points. 160 is the Einstein quotient. So we may calculate probability that a 10 students IQ of 10 students may be more than 150, that is p of x greater than 150. Okay, for these kinds of instances we'll be supposed to use normal distribution and normal tables to calculate the probabilities. Okay, so now here you're observing a graph. Okay, what is this graph? This graph is nothing but the graph of the density function 1 by sigma root 2 pi e power minus 1 by 2 x minus mu by sigma whole square, that is the normal distribution. So when we plot the normal distribution f of x represented by 1 by sigma root 2 pi e power minus half x minus mu by sigma whole square, okay, here you can understand that this is an exponential function and x is a real number, okay, and this is constant, pi is a constant, root 2 is a constant, and sigma is a parameter. Okay, when you plot this graph, the progression of the graph will be like this. The progression of the graph will be like this, which is like a bell shaped curve which is placed reverse. That is, if you place a bell, temple bell, okay, if you place a temple bell in the reverse form, in the yeah, if you place a temple bell in the reverse form, you will get the normal curve shape. That means normal curve is like a bell which is a temple bell, okay, which is like a temple bell reverse, okay, and you can observe that it is equally divided. It is exactly divided at the middle position mu. That means the entire normal curve will be equally divided into two parts at the point mu, which is nothing but the mean or the important parameter of the normal distribution. And that means you'll have both sides equal areas. That means if this part is 50%, then this part will be 50%. If the right side is 50 acres of land, then the left side is also 50 acres. That means equally occupied on either side of the line x is equal to mu. That is symmetric. That is what we have discussed. When we are discussing skewness yesterday, we discussed this. So normal distribution is a perfect symmetric curve. It will not be positively stretched or negatively stretched. It is perfectly stretched. That is why both sides we are having equal areas, 50 acres, 50 acres, like that. And here we are having some important boundaries. See this, mu minus sigma and mu plus sigma. Okay, and Here again we are having another pair of boundaries, mu minus 2 sigma and mu plus 2 sigma. Again here we are having a pair of boundaries on either side of the middle part mu, that is mu minus 3 sigma and mu plus 3 sigma. What does these boundaries indicate? The boundaries tells us that the area the area under normal curve between the first two boundaries is almost 68%. That means if you feel that the area under normal curve is suppose 1 acre, the total area is 1 acre. Okay, 68 cents will be lying between mu minus sigma to mu plus sigma, where mu is the center or mean, sigma is the standard deviation. So 68% of the area under normal curve will range between mu minus sigma to mu plus sigma. And if you take the second pair of boundaries, mu minus 2 sigma, mu plus 2 sigma, you will get almost 95% area will be covered. Out of total 100 cents, 1 acre means 100 cents. Out of 100 cents of area, 95 cents will be 95% of the area will range between mu minus 2 sigma to mu. That means this entire area will be 95%, and that area will lie from mu minus 2 sigma to mu plus 2 sigma. Okay, and mu minus 3 sigma to mu plus 3 sigma, you will get almost all the area, that is 99% area, 99%. So these boundaries will specify how much area under normal curve will range. Mu minus sigma, mu plus sigma, these are called first sigma limits. Mu minus 2 sigma, mu plus 2 sigma, these are called second sigma limits. Mu minus 3 sigma and mu plus 3 sigma, these are called third sigma limits. And the first pair will give you 68% of the total area under normal curve, and the second pair will give you 95% of the total area under the normal curve, and third pair will give you 99% of the area under normal curve. Okay, now let us see some more interesting properties of normal curve. You know what? The total area under normal curve is always unity. Can you guess why? Why the total area under normal curve is unity? Unity means simple. The total area, that means this entire area, the entire area under normal curve from the beginning to the end will be either 1 acre or 1 hectare, okay, or 1 cent. It can't be 2 hectares or 3.5 acres. It can't be like that. It will be definitely 1 acre or 1 hectare. Why it is always unity? Simple. The logic is very simple. Since it is the graph of the function f of x 1 by sigma root 2 pi e power minus 1 by 2 x minus mu by sigma whole square, which is a probability density function. Remember, this is a probability density function. And probability density function always satisfies two conditions. That is, probability is always positive, okay, and sum of all probabilities, that is sum of all probabilities is always equals to 1. Sum of all probabilities is our total probability will be 1. That means total area under normal curve should be unity. Because sum of all probabilities is 1. Because all these are probabilities. Okay, all the points below this curve are probabilities, represent probability. That means sum of all probabilities 1 means the total area is unity. Okay, of course we'll prove it as a theorem. Now we are going to see some other important properties. Yeah. So as I told you, the curve is bell-shaped. Bell-shaped means it's like a temple bell. Okay, placed reverse. And it is symmetrical. Symmetrical means it is equally stretched around the line mu, x is equal to mu. That means right side 50%, left side 50%. Okay, and the skewness is 0 because it is equal stretched on both sides. Skewness perfectly symmetric, skewness is 0. And mean, median, mode, this is an important point. The mean, because it is perfectly symmetric, mean, median, and mode all will coincide. That means mu is mean and mu is median and mu is mode itself. The mean is mu, the median is mu, and the mode is mu. All the three things will coincide for the normal distribution. That is a special property. And the curve is asymptotic to the x-axis. See, this is a very interesting thing. If you see this graph, if you extend the graph along with x-axis, okay, sorry, here, a little correction. I'm going to see this. If you see the graph of a normal curve, if you see the ends, the terminals, it is like it is going to very close to the x-axis as you move on, but it never touches x-axis. That means it's like it is like asymptotic means it seems that they will touch at some point, but they never touch. Like if you see our sky and earth, if you see from a corner, uh, when you are standing on a beach, and when you observe, you will find that our sky and earth are meeting somewhere. They are meeting, but they never meet. In the same way, the x-axis seems to be touching the normal curve at some point, but it never touches. They get closer and closer and closer, but they never touch each other. That is called asymptotic nature. And x-axis is an asymptote to the normal curve. That means it is a tangent at infinity. It is a tangent at infinity. Okay, that means it never touches the curve, but it seems to touch at somewhere. That is what asymptotic. And the curve has points of inflection at mu minus sigma and mu plus sigma. Let me explain it carefully. Mu minus sigma and mu plus sigma. See, at this point, at this juncture, generally, mu minus sigma and mu plus sigma, the convexity means openness, concavity means closedness. Okay, so the curve changes its nature from convex to here, up to here it will be convex, but here onwards it becomes concave. Again, from mu plus t till mu plus sigma it will be concave, and from here onwards it becomes convex. That means it changes like this: convex, concave, convex. So at mu minus sigma and mu plus sigma, it changes its nature. It changes from convexity to concavity, and again it changes from concavity to convexity. That is what we observe. Okay. And of course, we'll see these things. Odd, we can calculate mu1, mu2, mu3, etc. These are called moments. Moments can be calculated to MGF. Of course, we are going to derive the MGF of standard normal distribution in few minutes. Okay, and you know how to calculate moments by differentiating. I told you yesterday d by dt of moment generating function, and putting d is equal to 0 gives you mu1, and 2 times derivative putting t is equal to 0 gives you mu2. Like that you can calculate these moments. If you calculate these moments, you will get mu1, mu2, mu3, mu4, mu5, so on. See, mu1, mu3, mu5 are called odd events. Mu2, mu4 are called even events. Now, as far as the normal distribution is concerned, all odd ordered moments, that is mu1, okay, mu1, of course here mu1 dash, you can write mu1 dash, mu2 dash, mu3 dash, mu4 dash, mu5 dash. Okay, all odd ordered moments will be zeros, and all even ordered moments can be obtained through this formula. That is what it is saying. Okay, and R means the index. Suppose if you are calculating mu4, it can be written as mu2 into 2. This is R. Okay, this is R. Okay, and sigma is standard deviation. So what it says, the odd moments are always 0 for a normal distribution, but even ordered moments can be calculated with this formula. It's just a property. You can just remember it as a form. Yeah. And what about the kurtosis of normal distribution? Let us see. If you see, the normal distribution curve is like a reverse bell shape. It is equally stretched, that is perfectly symmetric about the line x is equal to mu, and mean, median, mode all will equal. Okay. And if you see, this is mesokurtic. That means it is not too high and less, and means narrow at the terminals, and it can't, the curve is not like this. The curve is not like this. If the curve is like this, we call it as leptokurtic. This is leptokurtic. This is mesokurtic. And the curve is not like this. This is called platykurtic. Platykurtic. So leptokurtic, mesokurtic, platykurtic. But our normal distribution will always mesokurtic. That is balanced height and balanced stretch. Okay. So that is why it is mesokurtic. Okay. And this is, I already told you, 68% of the area will lie between mu minus sigma to mu plus sigma, and 95% of area will be covered under the limits mu minus 2 sigma to mu plus 2 sigma, and 99, almost 100% area will be covered from mu minus 3 sigma to mu plus 3 sigma. Okay. Now, this is a standard normal variate. Let us see how this is written. First, let us consider a general normal variate. F of x is equal to 1 by sigma root 2 pi e power minus 1 by 2 x minus mu by sigma whole square. Now, let us substitute x minus mu. Let us imagine that x minus mu by sigma is z. Then what happens? Let us check. E of x minus mu by sigma is equal to E of z. You know, sigma is a constant. It can be written as out. So 1 by sigma E of x minus E of mu. E of constant is constant. So it is mu is equal to E of z. And x is a normal variate. X is a normal variate. X follows normal distribution, right? X follows normal distribution. So the normal mean is mu. Normal mean is mu, which we are going to prove. So mu minus mu is equal to E of z, and hence this is 0. E of z is 0. Similarly, you can understand, you can calculate when you substitute x minus mu by x minus mu by sigma with z. When you replace x minus mu by sigma with z, the distribution will be, the variance of z will be 1. And hence, this entire function will be changed to a new function. Pi of z is equal to 1 by, because sigma, that is variance is 1, sigma will be 1. So 1 by root 2 pi e power minus z square by 2, which is known as the standard normal variate. So standard normal variate is nothing but, let me write it more clearly. This is a general normal distribution function, that is 1 by sigma root 2 pi e power minus x minus mu by sigma whole square into 1 by 2. And if you put mu is equal to 0 and sigma is equal to 1, it will be reduced to f of z 1 by root 2 pi e power minus z square by 2. Okay, that means if you put mu is equal to 0, sigma is equal to 1, and x is equal to z, you will get a new function. This is called standard normal variate. Okay, whose mean is 0 and variance is 1. Yes, this is the graph of normal standard normal variate. This is 0 because here mean is 0, mu is equal to 0, sigma is equal to 1. Mu minus sigma means 0 minus 1. Mu plus sigma means 0 plus 1. Mu minus 2 sigma means 0 minus 2. Mu plus 2 sigma means 0 plus 2. Like that, you can understand. The same properties will be applied here. except mu is equal to 0 and sigma is equal to 1. That's what we have to understand. Now, uh, here we are going to write an important thing, that the variance of a, suppose n x follows normal distribution mu comma sigma square, that is f of x is equals to 1 by sigma root 2 pi density function e power minus half x minus mu by sigma whole square, then the mean, that is e of x, will be equal to mu and v of x will be equal to sigma square. So here in this theorem we have written the variance of x is sigma square, that I am going to show. Before that, I'd like to derive the mean of normal distribution. Then we'll go to the variance of normal distribution. So let us start it like this. First, let us write the density function PDF of a normal distribution. That is 1 by sigma root 2 pi e power minus 1 by 2 x minus mu by sigma whole square. Okay, and let us start with the expectation e of x. Expectation is 1 by, let me write the definition. Expectation of x is nothing but minus infinity to infinity x into f of x dx, which we have discussed in the last classes. The expectation of a continuous random variable is nothing but minus infinity to infinity x into f of x dx. This formula will come across in your probability and statistics course, which you have studied in your second semester. Now, after writing this formula, let us substitute the value of f of x, that is 1 by sigma root 2 pi e power minus 1 by 2 x minus mu by sigma whole square dx. Okay, we have substituted the f of x value. The f of x value is substituted over here. Now, what is the variable? Variable is x. So this is constant. Doesn't contain x, so it can be written outside. So we'll get 1 by sigma root 2 pi integral minus infinity to infinity x e power minus 1 by 2 x minus mu by sigma whole square dx. Okay, now let us try to substitute. Substitute 1 minute. I'll rewrite it more clearly. So we have arrived at this situation. E of x is equal to 1 by sigma root 2 pi minus infinity to infinity x e power minus 1 by 2 x minus mu by sigma whole square dx. Now let us assume that let us substitute x is equal to sigma z plus mu. What we are substituting? While integrating, we'll use substitutions. We are substituting x as sigma z plus mu. Okay, then let us see what happens. If we substitute this, the integral becomes 1 by sigma root 2 pi minus infinity to infinity sigma z e power minus z square by 2. Okay, and when you use this substitution, dx will be equal to sigma dz. Okay, that is why this becomes sigma dz plus minus infinity to infinity mu into e power minus z square by 2 sigma dz. Okay, that means we have split the integral. We have substituted x, we have substituted dx, and we split the integral into two integrals. Then what we observe once we multiply with this, we observe that 1 sigma by root 2 pi integral minus infinity to infinity z into e power minus z square by 2 dz plus 1 by root 2 pi integral minus infinity to infinity mu e power minus z square by 2 dz. Now we arrived at an interesting situation. Let us recap one formula from your Fourier. I think when you are doing Fourier series of transforms or in your intermediate integration, you might have come across this formula. That is, when the function is even, suppose g of x is even, minus infinity to infinity, g of x dx becomes 2 times of 0 to infinity g of x dx. And if g of x is odd, then minus infinity to infinity g of x dx will be 0. This is a very well-known formula in our definite integration. I'll rewrite it, just you can understand it in a simple way like this. Integral minus infinity to infinity even function dx will be equals to 2 times of 0 to infinity even function dx. Integral minus infinity to infinity odd function dx will be equal to 0. Okay, so that is why by using this formula, if you see here, z is an odd polynomial, that is why this is odd, and z square is even, so e power z square is also even, so this is even. Odd into even always results into odd function. Odd into even is odd, odd into odd is even into odd is odd, even into even is even. You know this. So odd function into even function will be an odd function. So minus infinity to infinity odd function integration is always 0. That is why this integral becomes 0, because this is odd. This is odd. Minus infinity to infinity odd function integration is always 0. That is why this becomes 0. And here this is even. This is even function because z square is even. That is why this is even. And due to that, this becomes mu by root 2 pi 2 into 0 to infinity e power minus z square by 2 dz. Okay. And from your special functions, that is gamma, beta, those kinds of functions, there are formulas like gamma functions, beta functions. Okay. From that we have a formula integral 0 to infinity e power minus x square by 2 dx is equal to root 2 pi. So no, it's a root pi by sorry. The formula is root pi by root. Okay, so 0 to infinity e power minus x square by 2 dx will always be equals to root pi by root 2, which is a result from gamma functions. Okay, we are using that result as a formula, and this becomes 2 mu by root 2 pi into root pi by root. Then root 2 cancels, root pi cancels, the answer is mu. So finally we have proven that the expectation of the normal distribution is mu. That means the mean of the normal distribution is mu. That is what we have proven. Okay. Now let us move to another important result. We are going to show that the total area under normal curve is unity. So for this, let's take, that means we are going to show that integral minus infinity to infinity f of x dx is equal to 1. For this, we'll start like this, minus infinity to infinity 1 by sigma root 2 pi e power minus 1 by 2 x minus mu by sigma whole square dx. Now, this is a constant, it can be written out. So 1 by sigma root 2 pi minus infinity to infinity e power minus 1 by 2 x minus mu by sigma whole square. Now you can easily observe that this is even. Why? Because this is a square, x minus mu by sigma whole square. So this is even polynomial. Even polynomial is also even function. So this is an even function. Since it is an even function, we get 1 by sigma root 2 pi. Okay, minus infinity to infinity even. That means 2 into 0 to infinity. The integrand, that is minus half x minus mu by sigma square. Just now we discussed a formula from gamma functions. With that, this becomes 1 by sigma into root 2 pi into 2, and this becomes root pi by root 2. Just now we have used it in expectation of x theorem. So that the same formula we are using, gamma functions. Okay, this integral will be equal to root pi by root. And root 2 cancels, root pi cancels. Okay, and here one more thing we forgot. Sorry, let me just yeah, see this here. Now we forgot to substitute. Let us substitute z x minus let us substitute x minus mu by sigma is equal to z, then dx is equal to sigma dz. Then it becomes 1 by sigma root 2 pi 2 into 0 to infinity e power minus z square by 2 sigma dz. So sigma cancels, and this is an even function. So this has from gamma functions we have a formula 2 by sigma root 2 pi. This integrand becomes root pi by root 2 from the gamma function formulas. Root pi by root 2. And you know, root 2 cancels, root pi cancels, and answer is 1. So that is what we have proved. That is total probability is 1. That is total area under normal curve is always unity. In the same way, by using the same logics, you can also prove that the variance is of normal distribution is sigma square. The same logic, same substitutions, same kind of gamma function formula, you can prove that the variance of the Gaussian distribution is sigma square. So these are important aspects of the Gaussian distribution, where we have discussed various properties. That Gaussian distribution curve is reverse bell shaped, and it is symmetric about x is equal to mu. It is perfectly symmetric. It is mesokurtic. It stretches from mu. There will be 3 boundaries: mu minus sigma, mu plus sigma, mu minus 2 sigma, mu plus 2 sigma, like that. Here 68% area, 95% area, 99% area, and these are points of inflection. This is asymptotic, and median mode will coincide. And after that, we have proven that expectation of normal distribution is mu, and variance is sigma square, and total area under normal curve is unity. These things we have. With this, we have successfully completed the theoretical side of the Gaussian distribution, and in the next video, we'll come with some applications of Gaussian distributions. We'll come with some problems. Okay, thanks for your patience. Thank you all.
Like, share and subscribe. Hit the bell icon for more updates.